This is our ISL brown bag talk. So thanks much for joining this session. And today we're very happy and honored to have Dr. Jackie Zhang to join us in this speaker series. So Dr. Zhang is a associate professor from FSU College of Education, Health and Human Sciences. She's a quantitative methodologist whose research addresses core issues across social sciences. She actively collaborates on projects spanning psychological, educational, and medical domains, and her expertise covers a wide range of pressing topics critical for applied researchers, including causal inference, longitudinal analysis, mediation and moderation analysis, machine learning for variable selection, missing data, meta-analysis, within-person effects, and multi-level data analysis. Her rigorous quantitative work is consistently published in top-tier journals. For her significant early career achievements, Dr. Zhang was honored with the Anastasia a Distinguished Early Career Contribution Award from the American Psychological Association. So today, Dr. Zhang will be talking about causal mediation analysis. Please take over, Dr. Zhang.
Great. Oh, thank you, Dr. He, for the introduction, and it's my pleasure to be here with you all today. And today I'm going to share with you an introduction to causal mediation analysis, which aligns with one of my focal research areas in causal inferences. Before talking about causal mediation analysis, let's take a quick look at causal inference in everyday lives. Right. So it actually exists in everyday lives, and you probably make or imply causal relations in everyday conversations. For example, drinking coffee improves my productivity, exercising makes me lose weight, eating organic foods leads to better health, or pollen in the spring triggers allergic symptoms. So next question I want to address is, when are causal inferences legitimate? So just use the everyday example as an illustration. Let's say, suppose Jake had allergic symptoms when pollen appeared, and these symptoms disappear past the blossoming season. Suppose all the other things being equal, so no other factors have changed except the time, the season. So my question for you is a quick vote. Did the blossoming of plants and pollen exposure cause Jake to develop allergy symptoms? If you think yes, can you answer yes in the chat? If you think no, please answer no in the chat. I'm taking a look. So far, I have about half yes, half no. So let's cut to chase here. The answer is yes. We can make a causal inference because we made this. Let me put on my phone here. We made the assumption that all the other things are equal, so no other factors are contributing to the symptom change except the season. So now we can tease out the impact of season on Jake's allergic symptoms. Now, I have a different example now. Suppose Anne did not have allergic symptoms when pollen appeared, which also did not appear past the season. Again, all the other things being equal. So my question here, again, a quick vote. Did blossoming and pollen contribute to Anne not experiencing allergic symptoms? Yes or no? So this time I get consistent answer, no. Yeah, you're right. You're all right. No. Why is it no? Why no? Why blossoming and pollen did not lead to allergic symptoms? Not experience allergic symptoms because we can easily think of other factors that can also contribute to Anne not having allergic symptoms, such as her like genes or immune systems, right? Which cannot contribute, also more importantly contribute to Anne not having allergic symptoms. All right. So this is just like causal inference in everyday life examples. Now, let's take a look at causal inference examples in research. So in social and behavioral science research, many central questions are related to causality rather than association. They will give you some examples. In lifestyle and longevity studies, does smoking cause lung cancer and earlier mortality? So this is a well-known question and also well-studied question. And another example, diet and metabolic health. Do sugar-sweetened beverages cause obesity and type 2 diabetes? Another example in psychology, does social isolation lead to cognitive decline? So those questions are prevalent actually in social science research. You can find many more of those examples in your field probably. So researchers often care about the causal effect and oftentimes how and why a treatment or intervention affects the outcome. So we can basically summarize the question in this figure below. So basically, let's say our problem can boils down to this. We want to see whether and how a treatment affects an outcome. So here a treatment is more broad. It can be any factors triggering the changes in outcome in a causal way. So probably we not only want to know if this causes an outcome, but also want to understand in the black box, in the process of how this treatment causes the outcome to change. And that's my focus of the talk today. So basically, to answer the how and why question, we resort to the so-called mediation analysis. So mediation analysis uncovers the underlying causal mechanisms. According to the definition by the classical paper at Baron and Kenny in 1986, mediation represents the generative mechanism through which the focal independent variable, say the treatment, can influence the dependent variable of interest, the outcome. Now, effectively, the treatment effect or the causal effect can be decomposed into an indirect effect that's transmitted through this hypothesized mediator and which can then in turn impact the outcome. And also a direct effect representing the part of the causal effect via other pathways. So we just use this path directly from treatment to outcome to depict the direct effect. That's not contributed by this mediator here in this path diagram. Now, let's use one example to walk through the whole illustration about causal mediation analysis. So in this example, we want to use diet as a treatment, and the outcome is cardiovascular health. In short, I use cardio health. And I not only want to know whether diet causes cardio health, but also I want to know how diet causes cardio health. Let's say we hypothesize that BMI, body mass index, is a mediator. So this says diet causes cardio health through its impact on BMI. So this is the mediator. This explains how there's a causal effect from diet to cardio health. So in this example, the indirect effect is the improvement in cardio health through BMI's decrease. And the direct effect is the impact of diet directly on cardio health without changing patients' BMI levels. We'll see more examples coming up, okay? So next I want to introduce to you different methodological frameworks of addressing the mediation analysis problem. So basically, in the conventional framework, it's usually involved assumptions about the models that's involved to depict the relations among those variables. So to depict the relations among the treatment, we use T to denote treatment, the mediator, and then the outcome. People often use in the past linear modeling framework. So if you're familiar with regression models, we can say that the mediator, in this case BMI, is predicted or is explained by the diet, the treatment. So that's this path. And in addition, our outcome cardio health is predicted or explained by the diet, the treatment, and also the mediator. So we can use another regression model to depict the relations between T and M and Y here. So this, as you can see, we put assumptions on the models for addressing mediation, which is a linear assumption. So in order to get the mediation effect quantitatively, we have mainly two different ways. You can use the difference methods, which says that basically if you have a total treatment effect from diet to cardiac health, so we know how much diet causes a change, how much change diet causes in terms of cardiac health versus not having this diet treatment, right? That's the total effect, C. And C prime, as we explained earlier, is the direct effect. That's the effect of diet on cardiac health, not attributing to BMI here. So the difference between the total effect and the direct effect is then the indirect effect, or the part of causal effect explained through BMI. And the other method we could use is the product method, which is basically if you obtain the estimate from treatment to BMI to the mediator, which is A pass, and then you get a pass also from BMI to cardiac health, which is B. You can take a product, again, assuming that your models are in these forms for M and Y. So as we explained, the direct effect is C prime here. And there are different kinds of statistical tests we could use to answer the question about to do the mediation analysis. So the tests include mainly the Sobel test, bootstrapping, and Monte Carlo simulations, among many others. So because we're not focusing on the conventional framework, I'm not going to talk in more detail about those methods, but let me know if you're interested in finding more about those methods. I can share with you the papers. But I'll tell you why I don't recommend this conventional framework in a moment. So why we don't recommend using this conventional framework to answer the question about mediation analysis. As I mentioned, we have to assume using this method that the relations among the variables are all linear, which may not be true in practice. I can give you some examples. When intervening in Alzheimer's disease via BMI, the relationship between BMI and Alzheimer's disease isn't linear. So both very low level of BMI and very high level of BMI isn't ideal, isn't beneficial. When intervening in work performance via stress, we found in ample research that relation between stress and work performance is not linear. So it's not good to have no performance. So in these two examples, you can see that the relation between those variables are not linear at all. And the other assumption we have for the treatment and the mediator in this pass, and there's no confounder between the treatment and the outcome this pass, and also no confounder between the mediator and the outcome this pass. So let's see whether they are legit. So if I was cut off a minute ago, probably I want to walk through this slide again. So so this slide just shows the drawbacks of the conventional framework, why it seems ideal. So first of all, the model have to be linear to use the conventional framework, but this may not be true in practice. So for instance, when intervening in Alzheimer's disease via BMI, the relation between BMI and Alzheimer's disease is not linear. And so I just said that it's not ideal to have both low level of BMI and high level of BMI towards Alzheimer's disease. And then in a different example, when intervening in work performance via stress, the relation between stress and work performance is not linear also, because we don't hope to have very low level of stress, no stress at all, or very high level of stress towards work performance. So in these two examples, the relation between the mediator and the outcome are not linear at all. So the second assumption is that under the conventional framework is that there's no confounders between the treatment and the mediator, so no confounder between diet and BMI, and no confounder between the treatment and the outcome, no confounder between diet and cardiac health. In addition, we don't have confounder in between BMI and cardiac health this pass. So let's see if those are legitimate. With random assignment, it's legitimate to assume there's no confounder between the treatment and the mediator because we randomly assign people into different groups. And also, similarly, we don't have to worry about confounders between the treatment and the outcome. Again, because treatment is randomized. However, is it legitimate to assume there's no confounder between the mediator and the outcome? No, it's not legitimate oftentimes because, like I say in this example, we can easily find some factors that can impact both BMI and cardiac health, for example, stress. Okay, so in this case, we are validating the assumption of no confounders between any of those paths in this modeling. So having talked about the drawbacks of the conventional framework, then I want to introduce to you a different framework to address the causal inference problems, which is the potential outcome framework or the counterfactual framework. The potential outcome framework, also known as the Rubin causal model, is the formal framework used in causal inference to estimate the effect of treatment or intervention on an outcome. So it helps answer the question of what would have happened if things were different. So what would have happened? What would have happened if you put people in treatment, in diet treatment, versus not putting them in diet treatment? Okay, what would happen in terms of outcome? So that's the question that's addressed under the potential outcome framework. It defines the causality by comparing what actually happened to what would have happened under a different scenario. So we call this different scenario a counterfactual. It's counter the fact that's actually happened. So then having said that, what are the potential outcomes? So basically each unit, for example, individual or group, if your interest is about the group, like schools, for example, or like clinics, they have two different possible outcomes for a unit I. So we use yi1 to denote an outcome if they receive treatment. And we use yi0 to denote an outcome if they are not treated, if they're in control. And so we will define the causal effect based on these potential outcomes across different units, different individuals. But before that, I want to give you an illustration through like my experience watching this movie. It's a movie I watched with my daughter in the last Christmas, it's Christmas Carol. So, to give you a brief like background introduction about the movie. So this main character, this person, Scrooge, he initially was a cold-hearted, greedy miser who despises Christmas, and he got his redemption by visits from the ghost of Jacob Marley, his friend, and the ghost of Christmas past, the ghost of Christmas present, and the ghost of Christmas yet to come. And the Christmas, one part I remember very vividly is the ghost of Christmas yet to come shows Scrooge where his greed and selfishness will lead. Basically, a lonely death and a neglected grave, unpaid, servants stealing his belongings, debtors relieved at his passing. And his employee, the Cratchit and his family devastated by the loss of their son, Tiny Tim. So Scrooge asked the spirit if this future can still be changed and begs for another chance and promised to change his ways and finds himself in his bed on Christmas Day. So next I'm going to show you what would happen if he changed and what would happen if he did not change versus what actually happened because of his change. So one thing is this. So this is one contrast if Scrooge does not change his mind. His employees, Cratchit. The overworked unpaid clerk, Bob Cratchit, and he symbolizes the poor working conditions, especially long working hours and low pay. If Scrooge doesn't change, the Cratchit family will keep struggling to live. This is his family during Christmas Eve. So after Scrooge decides to change his ways on Christmas Day, after seeing what would happen if he didn't change, on Christmas Day, the next day, he anonymously sends a Christmas turkey to the Cratchit family. And then the next day, Scrooge states that he will increase Cratchit's salary immediately and promise to help his struggling family. So this is what's actually observed. This is their son still happy and alive after he has changed. So this is what actually happened, the observed. And this is what's not happened if he had not changed, if he remains the same guy. So this is counterfactual. In a different scene, Scrooge first refuses his nephew, this is his nephew, Fred's invitation to Christmas dinner and denounces him as a fool for celebrating Christmas. And after the visits of the ghosts and things Scrooge sees, if he doesn't change, this is when people are talking behind Scrooge, about how he behaves. And this is what actually happened after he sees this, if he doesn't change. And see his happy face with all the guests of his friends and his nephew enjoying Christmas dinner. So this is again observed what's actually happened, and this is what would have happened if he had not changed. Okay, so it's two contrasting outcomes. So I hope you get a rough sense of what a counterfactual is and how we use this to compare to what's actually happened. So also bear in mind, we don't observe the counterfactual. This is what would have happened. Now then, based on the counterfactuals, Y1 and Y0, for the same individual of treatment and control groups, respectively, we in our example, how we define them. So in our example, Y1 and Y0 are the two potential cardio health scores when diet treatment is provided. This is one is provided and the one is not provided. So the treatment effect for an individual I is then, for individual I, is defined as yi1 minus yi0. However, as we mentioned, for each unit, we can only observe one of these two potential outcomes, but not both. Only one of them is observed, either this one or this one, but we cannot get both of them. So that makes this definition useful, but not applicable. So therefore, oftentimes the average treatment effect is the focal interest. So we take an average of all the Y's in treatment and in the control group to get this ATE, estimate of causal effect. So delta is defined as expectation Y in treatment minus expectation Y under control. So we usually use this definition to define the causal effect. So in this simple example I made up, so basically we have the outcomes in this column and the treatment condition in the first column for those individuals. So basically, the potential outcome column is in the control condition, and then the potential outcome is in the treatment condition. We can just tease the observed outcome into those two different columns. So basically, what's in black numbers are actually observed in this column. And what's in red here are not observed, but suppose we know them. So those are the counterfactuals we did not observe. And so if you know them, you can define each individual's causal effect in this last column. But as I said, this is ideal case. We don't know. We won't never know both the potential outcomes in both conditions. So that's then drives us to the next thing to discuss. So we have to have assumptions because we cannot observe all the outcomes in both in control and treatment groups. So we do have to have some assumptions to make sure our causal effect estimate is good. And so those assumptions, mainly we have three major assumptions for estimating causal effects. The first one is called the stable unit treatment value assumption, or in short, a SUTVA assumption. It has basically two different components. The first component is that the treatment assigned to one individual doesn't affect the outcome of another individual, so meaning no interference among the individuals. So if interference exists, then the estimated treatment effect, it may be biased. To give you a counterexample, if a patient receiving a diet treatment shares advice from the treatment with their friend who did not receive the treatment, then the control group is indirectly treated. So that will impact the causal effects. The second component of SUTVA assumption is that there are no hidden versions of the treatment. So basically, each unit in the study receives a well-defined treatment or control condition, and the treatment is the same for all the units that receive it. So if individuals receive different treatment variations, then we can't determine the causal effect, resulting in inconsistent results. Now, suppose a study evaluates impact of low carbohydrate diet, a particular kind of diet, on cardiovascular health. And the possible variations I can think of can be, for example, healthy fats, like using olive oil in their diet, versus saturated fats, like cheese. So both are like different forms of low carbohydrate diet, but as you can see, those are different versions of treatment. So using different versions of treatment may lead to different cardio health outcomes, actually. So this is the violation of the assumption, the Stella assumption. The second assumption is the strong ignorability assumption. So basically, this says that given conditioning on the pre-treatment covariates, the potential outcomes are independent of the treatment. I mean, to interpret it in a different way, basically, before the treatment starts, before it's implemented, all the individuals, all the units, they are comparable in terms of their outcome. So there's no difference in terms of the treatment outcomes before the treatment. So conditioning on the covariate, then this is as good as random assignment. So meaning no unmeasured confounders affect both the treatment assignment and the outcome. So this ensures that any differences in the outcome between the treated and control groups are caused only by the treatment, not by any pre-existing differences. So as I said, the individuals are comparable before the treatment, and difference only is due to the treatment, based on this assumption. For example, patients with better health education are likely to understand nutrition labels and cooking skills more effectively, and they tend to have good health habits. Therefore, health education has a positive impact on both diet quality and cardiovascular health. So you can regard health education to be a pre-existing factor that can contribute to people not comparable before the treatment. This is validating that assumption. And a commonly used method to deal with the potential violation of this strong ignorability assumption is the sensitivity analysis, which I'm going to show you an example later on. What is that? This. The third assumption of the causal effects is an overlapping or positivity assumption. So this says basically each individual has a positive probability. They all have a chance of being in both treatment and control groups, given their covariates X. So when the overlap assumption is violated, then some individuals have near zero or near one probabilities of being in either one of the two groups, meaning they're almost always treated or almost always untreated. So this cannot allow us to make a comparison between the treatment and control groups among those individuals. So for example, if a healthy diet is only available to patients with a BMI bigger than 30, then we cannot estimate the effect of diet on cardiovascular health for other patients because they never receive treatment. So those are the three assumptions we have to assume to have a good estimate, causal effect estimates. Next, let's see an application of the assumptions in a real example, and not a real example, a made-up example following on my earlier small data set. So here, based on the assumptions, if all the assumptions are satisfied, then we can define ATE as expectation of Y in the treatment minus expectation Y in control. So meaning taking averages in treatment, taking averages in control, and do the subtraction, we will get the ATE, average treatment effect, legitimately. So particularly this applies the ignorability assumption. So basically, everybody are comparable before the treatment starts. So that's why even though we don't observe their outcomes in control or in treatment, those individuals are comparable before the treatment. So we can say that those available scores are representative of the control condition, and those scores observed are representative of those in the treatment group. So essentially, effectively, you should have observed averages under control and under treatment to be the same as those true averages. If you observe those potential outcomes, all the scores observed. So basically, ultimately, you will have the same causal effect as a true average same causal effect under observed average as the true average, basically. So this is a good estimate. Now, having said that, I want to also list some major methods to estimate causal effects, as there are a lot of methods. So I want to summarize them into a few categories. So I just mentioned an example when people are randomized or like RCT trials, right? So what would happen? What can we use if those people are not randomized? So basically, one major method is called the propensity score-based method. And the propensity scores are often used to estimate the causal effects without RCTs to address the selection bias issue. So basically, it's defined in this way. It's the probability of receiving a treatment given the observed covariates. For example, it's the probability of receiving diet given like socioeconomic status. What's the chance that the person receive treatment given his or her SES status, right? That is the propensity score. So once it's obtained, it can be used to estimate the causal effects. The major methods include matching, stratification, and inverse probability weighting. So there are many different methods you could use, and there are many different models you could use to model the propensity scores. So other major methods you could use include like G methods, which focuses on the models of the outcome, like how we best model the outcome. And also design-based approaches such as DID differences. Design, this involves two time points, usually speaking, and RDD, regression discontinuity design, and instrumental variables. So people can design their study to make legitimate inferences about causal effects that account for the confounders or addresses confounders. And also sensitivity analysis. I mentioned already, sensitivity analysis is a very important technique to be used under causal inference. So it's mainly actually used to address the unmeasured confounder problem. So for a list of software and propensity score analysis and sensitivity analysis, I would recommend Dr. Elizabeth Stewart's webpage, which this webpage contains the packages, R packages, and code to implement propensity score analysis and sensitivity analysis. So if you're interested, please visit the website and see if that can help you with your problem. So we are still going to focus on the conceptual part of causal mediation analysis after talking about the computation methods. So for causal mediation analysis is the next step of causal analysis, causal inference analysis. As I said, it addresses a question of how and why the treatment causes the outcome. So how diet causes cardiac health. But before that, our first research question usually is, does diet impact patients' cardiac health? You want to know if it causes cardiac health, and we want to know next how it causes cardiac health change. So the next natural question is, how does diet impact cardiac health through your hypothesized mediator, for example, BMI? Then we have to introduce some potential outcomes for the mediator and the outcome to address our question. So let's introduce some notations here. So M1 is the potential BMI for the mediator if assigned to treatment. M0 is the potential BMI if assigned to control. And so very similar fashion as what we saw before for Y. Now, what's different is this. So we have to introduce notation for the potential outcome, like Y, the cardiac health outcome. So now it has to be impacted by treatment and the mediator, so it has to have two components in it. Now, so Y1 M0 then is the potential cardiac health if assigned to treatment, but this individual's potential BMI takes its value as if this person is still under control condition, no treatment. So as you can see, this is not observed, this is counterfactual. And the Y0 M1 then is the opposite, is the potential cardiac health outcome if assigned to control. That's this 0 here. Well, the potential BMI mediator takes the value under the counterfactual treatment condition. So this M1 is is the value as if this person receives treatment, although he or she is in control group. So those are the two counterfactors we did not observe. But the observed outcomes are these two. Those are easier to understand. So Y1M1 is the potential cardiac health if assigned to treatment. So treatment 1 and M is also under treatment. So Y0M0 then is a potential cardiac health outcome if assigned to control. So you get control, and also the mediator is also got under the control group, the BMI value. Now, after introduction of those notations, let's take a look at how we can obtain the mediation effect in this potential outcome framework. So in this table, I've put in in the rows we have the potential outcome for the mediators, and then in the columns we have the treatment conditions. So then, borrowing our notation earlier, and then Y1M1 is the expected health outcome. It's not expected. It's a health outcome if the patient receives a diet treatment and their BMI, the mediator, is impacted accordingly by the diet treatment. So this is actually observed. Now, Y1M0 is the expected health outcome if the patient receives the diet treatment, this one here, but keeps the same level of BMI as if they had not received it. So then, based on these two quantities, the population natural indirect effect, we call NIE here, is also the mediation effect. It's basically the difference between the expected value of Y1M1 minus expected value of Y1M0. So the difference here is called the natural indirect effect. So it tells us how much health scores change due to the change of the BMI score. So now you can see the BMI scores have changed from the 0 condition to the 1 condition, treatment condition, but the treatment condition remains in the 1 condition treatment. So how do we interpret it in different scenarios? So there are different scenarios about this directions of this natural indirect effect. So in the first scenario, we may have a positive NIE. This implies that diet treatment indirectly increases cardiac health because it reduces BMI. So this is reducing BMI, which then increasing. A reduction in BMI then gives us an increase in cardiac health. So this is a positive NIE here. So this suggests that BMI is a key pathway explaining the effect of diet treatment. In the second scenario, we may have a 0 NIE. So this implies that diet treatment does not improve cardiac health through BMI. So this doesn't explain the causal path from diet to cardiac health. Then it suggests that cardiac health improvement can come from other factors, such as physical activity and alcohol consumption. You may find other legitimate mediators in this case. In the third scenario, you may have a negative NIE, which is not intended actually. So this implies that diet unexpectedly lowers cardiac health. For example, this could happen because like a sudden decrease in BMI may not be beneficial. It may negatively affect cardiac health. So it's not expected outcome. Next, I'm coming to another kind of research question. The RQ2, research question 2 is relevant to the mediation effect, and research question 3 is about the direct effect from diet to cardiac health. So for example, the question is, how much is the average causal effect of diet on cardiac health without changing BMI? So when BMI remains the same between the groups, how much this causes changes in cardiac health? So again, using the table, we're looking at these two components. So we're comparing Y1M0 against Y0M0. So as you can see, the mediator BMI remains unchanged at the control condition, like as if they did not receive any treatment in a natural condition. Then we're looking at the difference in the outcomes, in the expected outcomes between the control group and the treatment group. So this is defined then as expectation of Y1M0 minus expectation Y0M0. So it tells us how much the cardiac health improves due to diet treatment, independent of its effect on BMI. So when this does not change, how much this can cause cardiac health. So again, we can have different scenarios for this direct effect path. Right. So in the first scenario, we may have a positive NDE, natural direct effect. This implies that diet treatment directly improves health even when BMI is not changed. This suggests that diet also works through some other mechanisms such as blood pressure. So, which makes this non-zero and positive. And second scenario, we may have a zero NDE. This implies that diet does not affect health when BMI remains unchanged. This suggests that diet's entire impact on health comes from this mediator, this BMI here, and no other mechanisms are at play here. So this is the case when you find the key and only important mediator that can explain the causal path. In the third scenario, we can have a negative natural direct effect. This can imply that diet unexpectedly reduces cardio health when BMI is unchanged. So for example, diet increases stress, which worsens cardio health. That's not attributable to BMI here in this example. Now, in parallel to the assumptions under causal inference, we also have the parallel assumptions under causal mediation analysis, but this has to be extended. So, for example, for the step assumption, we just said it has two components, no interference assumption, but it has to involve the no interference regarding the mediator and regarding the outcome. So regarding mediator, the individual's potential mediator values do not depend on the treatment status of other individuals. For instance, it would be violated if BMI level of an individual is lower when both the individual and their family members are assigned to diet program than when the individual is assigned to the program individually. So if you put all the members in the treatment program, then that's a violation of the no interference assumption. Regarding the outcome, why? It says that individuals' potential outcomes do not depend on the treatment status or mediators' values of other individuals. For example, this assumption would be violated if an individual's cardio health depends on their family members' treatment assignment or their BMI levels. And the second component is that the no hidden variations of treatment. This is the same as before. So you have to have a consistent and clearly defined version of the treatment in your study. Okay, so second assumption is sequential ignorability assumption. We need this assumption to identify causal mediation effects as Y0 M1 and Y1 M0. They are not observed. So we have to have this sequential ignorability assumption. It has strong ignorability for the treatment. This means that there's no unmeasured confounders of the relation between the treatment and the mediator, and also the relation between the treatment and the outcome. So this can be achieved using randomization, actually. The second one is even stronger and unrealistic. It's a strong ignorability of the mediator. So it basically says that there's no unmeasured confounder of the relation between the mediator and the outcome. As we said, this is oftentimes not true. So this says you wouldn't have other confounders between M and Y. But we can think of some confounders that can impact both, like socioeconomic status. It can impact both BMI and cardio health. The third one is still the positivity assumption. It said that within levels of the pre-treatment covariates, like demographics, everyone has a non-zero chance of receiving each treatment level, and everyone has a non-zero chance of taking each mediator value under each treatment condition. So this ensures that we can compare the potential outcomes. So a bit more on the illustration of the strong ignorability assumption. So this says basically we have all the confounders controlled. I mean all the confounders among the three variables, the treatment, the mediator, and the outcome, they're all controlled in our study. So for example, SES is controlled for to remove or to make the strong ignorability assumption valid. In the case when there is randomized with strong ignorability of the treatment, when there's no confounder between the treatment in M and treatment in Y, then we can remove this path then. So there's no X to T path. We just need to worry about the confounders between mediator and the outcome, like SES in this example. So with all the introduction of the framework and the assumptions, let's look at one simple example to see how we can estimate the treatment effect in real studies and how to do a sensitivity analysis, as mentioned earlier, to probe the robustness of the strong ignorability assumption. So here I want to demonstrate the use of the R package mediation for the analysis. So in the simple example, we have 4 variables that includes treatment, T, which has treatment, a diet and no diet conditions, and the BMI, which is the mediator, and cardio health is an outcome, and SES is the covariate. Those are all continuous variables, and those are standardized beforehand. And we have roughly half of individuals in treatment and roughly the other half in control. So showing you the steps of this thing in this example. So basically the first step is if you haven't installed those packages, install those packages and call those packages in your R code, and then load in the data in step 2. In step 3, we start fitting the models. So basically this involves fitting 2 different models, first for the mediator for BMI in this example. So if we use regression, and I'll tell you this isn't required, but I'm using this just for the purpose of illustration. So if you use regression models for both the mediator and for the outcome, it's using the LM function, you can predict or explain BMI using diet and SES. Basically, you control for SES here. And then diet has its effect of negative 2.39 in this case, so it's negative, it's expected because in treatment group, for treatment group, we expect them to have a lower BMI. And it's highly significant here. And for the outcome model, for like this 2 paths, basically, we use BMI and diet to make an explanation of cardio health while controlling for, again, SES. So now you can see these 2 coefficients for like this path from diet to the outcome. This is a direct effect, which is this number 0.5, which is not significant. Whereas for the path between BMI and cardio health, this prediction, it is significant here. And so it's also negative, meaning higher BMI results in lower health, worse health. Now, so after finishing the step 3, we can then conduct mediation analysis using the mediate function here. So you have to tell this function what your mediator model was earlier in the earlier step and your outcome model was, and tell this function what your treatment variable is, in this case this, and what the mediator is, in this case BMI, and the covariates you have. So here is just a specification of how we can obtain the inference, like this is based on bootstrap. We can obtain the confidence intervals based on the bootstrap. Okay, so here shows us the results of the average indirect effect and the average direct effect in 2 different rows. So based on this estimates, you can see that in this case, the average indirect effect it has a confidence interval between 0.15 to 1.57. It does not include 0 in it. So this suggests that you have a significant average causal mediation effect or a significant NIE, natural indirect effect. Whereas in the next row, you can see the natural direct effect is this number and is not significant. P-value is bigger than 0.05, and the confidence interval, it contains 0 in it. So it's not significant direct effect. So that's the interpretation of the results, assuming there's no unmeasured confounders. But oftentimes, I recommend that we also do another step of conducting sensitivity analysis, which is to probe the robustness of the results if you have unmeasured confounders. So the idea is that if you find out a so-called sensitivity parameter, in this case, I use the correlation between the residues of BMI and cardio health. So to the extent that correlation is not 0, that means you would have confounders that's not included between the mediator and the outcome. So the idea is that I vary this correlation from -1 to 1, and I also using the same procedure to estimate my mediation effect at those values and see if the results will change. And so the shaded areas tell us about the confidence band. So in this case, this plot demonstrates that the direction, which remember is positive direction, meaning diet causes a positive change in health through BMI. The direction doesn't change when the correlation is above 0. So like in this area, in this range of row, the causal mediation effect doesn't change its direction and inference results. Whereas when rho is less than 0, there can be a different direction in your results. So this suggests that the result is not sensitive to unmeasured confounders as long as these confounders So you mean that the confounder, unmeasured confounder could relate in different directions and cardiac pulse. So one example, and I don't know, think just intuitively, perhaps some exercise can help you reduce BMI, right? So so it relates negatively to BMI, but also it at the same time improves health.
May not improve the health. I'm with you. So thank you.
No, yes, sure. It can have a negative correlation in that case. Yeah.
I understand. Thank you.
Yeah, sure. Next, let's just have a small extension. Basically, we've defined the NIE and NDE in this ways, right? So those are the differences between these expectations. But note here, I did not have to specify models for Y or for M here. So basically, the potential outcome framework is theoretically does not depend on any models you use. So you can choose any models. Although I used regression model before, but you can choose other models because it's unlike the traditional framework, it's not model dependent. In some of my research, I've used machine learning modeling to relax that assumption, to relax the model assumption to make sure I don't let the model determine my causal effects. So you can use flexible modeling of both M and Y to make this potential outcome framework more beneficial. And so this is a big advantage then compared to the traditional framework, as I mentioned. So because we usually have to assume linear relations and predetermined relations under the traditional framework, which is not desired. And also this potential outcome framework can be extended to multi-valued treatments. For example, you can vary the policy intensities, you can vary the doses, different doses, and you still find differences between different doses. And also it allows to have time varying treatments. So although I put in static treatment in this example, in this whole talk, but it can be extended to also time varying treatments. In addition, potential outcome framework does not it does not require your outcome or mediator to be special variable types like continuous variable, like in the linear modeling framework. We can have different types of the outcome or mediator under the same definition of NIE and NDE. So those definitions will remain the same, even though you have different types of Y or M. So that's those. So I would just want to show you some advantages of the potential outcome framework in contrast to traditional framework and some extensions. So with that said, that's the end of the talk, and I'll also include some references for you to read if you're interested. And thank you so much for listening.
Great. Thanks so much, Jackie, for this really informative and very detailed and rigorous talk. And I know a lot of folks on this call are doing this type of research using intervention research, collecting data from either randomized control trial or observational studies, and they oftentimes have the same issues, whether certain variables can be used for as a moderator or mediator, and how to build models using this. So we can have a few questions. So if people have any questions, please feel free to open your mic and share ask question directly to Dr. Zhang.
I just had one. In the very beginning, you told us why the linear, assuming assumption method would not be applicable. But my question is, once you get the data that you receive from like a study like this, and you're able to form like kind of the curve that you did, do you then apply that to other areas dealing with health or diet or BMI?
So you mean still under the conventional framework, do I apply the same models to the other type of?
Yeah, given that the co-founders you would assume to be similar, that I'm kind of wondering, would this be a more applicable regression formula to use because you did share the same co-founders. I just wondered, you may be altering something, the BMI this time, that might be your outcome. I'm just kind of wondering, since it's all kind of the same circle, do you then try extrapolate a little bit from the evidence you already have?
That's a good question. So, the drawback of that I mentioned about the conventional framework is not is mainly about its assumption regarding the model, the form of the model. So you'd have to assume that the relation between treatment and BMI is just linear in this form, and the relation between these two are with outcome are also linear. So we have to assume that, like, for example, when BMI changes, cardiac health always increases or always decreases, right? There's only one direction, but it might be the case that when BMI increases, the cardiac health,
but not at the same rate as the other.
Yeah, it may decrease first, and then I don't know, maybe it levels off or something. It's non-linear.
And that's why I
right?
wondered, like, you have to start somewhere, but once you get a more accurate overall, a number of subjects, a number of studies, and it still proves to be true. It seems like this could be something that when you do a paper, or it should be something other universities should be able to, as a starting point, is what I'm thinking.
Yes, yes, that's a good point. If you have found via multiple studies and via your theoretical framework, you know that's only, I mean, this is linear relation, like BMI increases, always cardiac health decreases in one direction, then it's legitimate to assume a linear relation. And that gives us the most power to estimate the causal mediation effect, actually. And it's easily applicable to many researchers. But what I'm saying, I just want to put caution there because it's not always linear relations in all the research areas. Yeah.
And I did understand also, because I'm currently finishing a year-long study, a nutrition study, that there are so many variables, especially when they had a target of how many carbohydrates, how many proteins, how many fats. And if you're off, they're monitoring that constantly, how that could alter the results.
Yeah, so I mean,
Yes,
very good statement. I mean, so a lot of those models have to rely on assumptions. So we already have assumptions in the causal inference framework, and those have to be checked. And if we add more assumptions, like the model form assumption, I think we need to be cautious. Like, at least we try different forms of the models and see the results will change. This is just my opinion.
I was just wondering, because it helps me understand what they're doing for my study. I appreciate the time.
I saw Dr. Elizabeth Slate had a hand raised a few minutes ago. Dr. Slate?
Yes, thank you. Can you hear me okay?
Yep.
Yeah, great. Yeah, hi. Thank you for a very nice talk. I really enjoyed the perspective. Could you go forward a couple slides where you define the natural indirect effect?
Okay.
Oh,
Pictures again.
Yeah.
Okay, I need to go further. Next slide. Yeah, there we go.
Yeah, actually, this table is very helpful. So your definition of natural indirect effect, I think, is quite intuitive, that we should compute the difference in the mean outcome attributable to a change in the mediator when the treatment is set to 1, right? In other words, under the treatment, under the intervention.
Yes.
But if we focus on the remaining column, the last column of that table, I'm wondering if you could just comment on what we can learn from that. Do you find people sort of evaluating that to learn more about maybe the effect of the mediator itself, in the absence of treatment? Was that ever of interest in your work?
Yeah, that's an interesting question. I mean, to my knowledge, people oftentimes, most of the time, focus on comparing these two, not these two, but these two also if you look at the difference between these two, it also has a meaning, as you said. What would happen if you don't receive treatment, but only BMI changes? So sometimes people may also be interested in this. So I mean, I'm defining this natural indirect effect in like just following the common practice people have been using, because they most often they focus on the treatment condition. But in some special cases, if you can justify this is also interesting, the difference between this is also interesting, it can also be defined and estimated in this framework. Mathematically, it's a direct extension. It's not new. So I think the most challenge is how to make sense of it. How to make
I
sense of
agree. Yeah.
yeah.
Yeah. It's sort of like, what's the effect of changing BMI? But we didn't
Right.
have the opportunity to
Mhm.
randomize,
Mhm.
BMI
Yeah.
changes.
Right.
Just
look at
curious
those.
about that. Thank you again for your perspective, and thanks for the talk.
Thank you. Thank you for the question and listening.
Thank you. So I think we do have one question. So Neil, do you have a quick question before we look at the
Sort of
questions on the
quick
chat?
question. I'm just wondering about extending this to the case of multiple mediators. What assumptions do you have to make
Mhm.
in the case of more than
Mhm.
one mediator?
With more than one mediator, and so, but that's a great question. So so just to clarify, do you still focus on the potential outcome at like for each mediator, or you want to look at all the
Yeah,
mediators
because
simultaneously?
I'm looking for n equals, instead of n equals 1, n equals 2 to n equals n, m or whatever, potential mediators. Because often
Yeah.
when you're doing, we'll take the diet example, you could be changing a lot of potential explanatory factors. It could
Yeah.
be, blood pressure level, it could be BMI,
Yeah.
it could be heart rate, there are a whole bunch of things that could be playing, or blood pressure and so on. So
Right.
what assumptions do you have to make about the mediators? Is it that they have to be independent of each other, or can you allow for, sort of
Right.
moderated mediation, so to speak?
A great question. Great viewpoint. So, I think the answer is it really depends on what your interest is. So, if you're interested in like each separate mediation path, like I'm drawing here, so you want to know if diet, like if how diet causes cardiac health through BMI, first of all, then how diet causes cardiac health through blood pressure. Those are different separate questions. Then those are regarded as two parallel mediation paths. And so addressing each mediation effect will be similar like similar in their fashion. So the assumptions regarding the mediators then would be not so as long as those two mediators are not in sequential. Like for example, I don't have BMI causing blood pressure, and which then causes cardiac health. As long as it's not sequential, they're in parallel. I think the process would be similar to what I just talked here. But to
Right,
the extent,
so in other words, you need a more complex model to look
yes,
at kind of sequential effects between mediators. That it
yes,
first leads to X, which in turn or M1, which impacts M2, with
Mhm.
M1 and M2 either jointly or not jointly, it's M2.
right,
That's the final or mediator in the
yeah,
path between the treatment and the outcome.
yes,
I was
exactly.
thinking about the example because I'm a Black woman, and somehow or another, based on what you're saying, Mr. Charnes, they decided somehow that the high blood pressure, the diabetic, and the diet were all related, mostly in African Americans. I don't know how they got to that point, but from what you're saying, somehow they got to that correlation of all of them at the same time, all those ends.
Yeah. Right. So if that's the case, if there's sequential here, then we do need to have that assumption in the causal path. Like, yeah, so this is like, you want to be, yeah. So one assumption I didn't put out here is that you have to assume this is the causal path. Like it causes cardiac health only through BMI. But if there are other complexities here, like also through blood pressure, then this also need to be entered into the potential outcome model. So as additional there.
Sort of as a final comment on that, though, is that statistics aren't going to solve our inference problem. What we still need is a causal model of the mediating mechanisms within, for instance, in this case, for health outcomes, there are a whole bunch of potential pathways that you could be exploring down at the biochemical level all the way up to, psychosocial types of levels. It doesn't, you want to go into this with a much better underlying mechanism explanation of potential outcomes, because the potential paths that you could be exploring are very, very large, and you really need, in a sense, your mechanism to help define what the plausible pathways are that give you your final outcome.
Exactly. Ideally, people want to have a good idea about the hypothesized, mechanisms of how.
Exactly. Yeah.
Yeah.
Great. Thank you so much, Neil and Jackie. There's just one question, two more questions in the chat. One from Daniel Lamy, and his question is the process to select confounders in your analysis. How many confounders can you select for your analysis?
How many confounders can you select? You mean, do you want a magic number? I think it depends on the methods you're choosing. So for instance, I use machine learning methods. You don't have a limit for how many confounders you will have, because machine learning will handle the variable selection problem itself. So you won't have a limit. But if you use regressions, it has a limit, right? You cannot have as many confounders as you want to. So yeah.
So you have to choose like more important confounders based on the specific application.
Yes, you choose. If you use regression, you have to choose more important ones. And I recommend also adding the sensitivity analysis to probe the robustness results if you omitted any other confounders.
Thanks. And the final question from OHA, Dr. Wang, is about longitudinal data analysis, pre-cardio, post-cardio, pre-diet, post-diet, or pre-BMI, post-BMI. How can a model be able to fit those factors twice, pre and post, and in this mediation analysis?
That's a good question. So if you have longitudinal data, time-varying data, I know some researchers are researching on the time-varying treatment effects. So they most likely they want to focus on how time 1 and time 2 treatment are impacting the final outcome of interest. But in your case, you seem to focus on more on the change part, like how the pre and post change in, like say in BMI would lead to the pre and post change in cardiac health, right? So that involves in some newly defined variables, the change type of variables in your case. So if that's the case, I would recommend have let me see. So put it in, I think the framework would not change, but if you focus on change, then the variables will change their meanings, not BMI, but BMI change, like not cardiac health, but cardiac health change. So conceptually speaking, you can still use the framework, but with a different definition of those variables in this past diagram. I don't know if that makes sense to you. But frankly, I need to think more carefully about how to address the change score problem in this potential framework.
Sure. So certainly, OHA, please follow up with Dr. Zhang if you have follow-up question on this. Because in the interest of time, we do have to close the meeting. I'd like to thank again Dr. Qian Zhang for being here, giving this wonderful presentation. I do want to invite you to join our next Brown Back next week at the same time, Wednesday, 12 p.m. by Dr. Vivian Guo, Qianwen Guo from College of Engineering, and her presentation will be focused on accessibility for older adults, which is a data-driven optimization framework for transit route design. It's related to transportation. So again, thanks so much for all the attendance, and we'll just looking forward to seeing you all in the next Brown Bag talk. Have a nice day, everyone. Thanks so much, Chen.
Thank you.